Hello there. So in this video segment today, I'm going to work through the solutions to the Advanced Chemistry 2 problem set that I've left for you in my faculty data folder, focusing on acid-base problems. To review, to this point we've covered a lot of material in chapter 15, discussing what acids and bases are, proton donation and acceptance being the definition of acid and base behavior in the Bronsted-Lowry definition, that is. We've looked at a few reactions. We've learned how to find pH values. We've learned about pKa. We've learned a variety of different things related to acid-base equilibria. And on the problem set that I've prepared for you, there are a number of problems to go over all of those different topics. So I'm going to spend the next probably 20 to 25 minutes, hopefully, going through the solutions to each of these. I hope you'll have worked the solutions already and are really following along as a means to check your answers. But if not, this could serve as a tutorial for you as well as you try to work on some of these problems independently while I'm still away at the ACS meeting in San Diego. So before you get started, I want to make sure you have the worksheet ready to go with you because I'm only going to be writing tertiary comments about each of the problems on the board. And you're probably going to need your Ka chart if you haven't already looked up the Ka values, and then perhaps your textbook as well, since there are at least one compound that we need to look up in the textbook to get its Ka or Kb value. Okay? With that, let's look at the first question, which is to identify the conjugate base of each of these acids. So one of the most fundamental skills that we need to be able to do. So an acid is something that donates a proton, and when it donates that proton, it eliminates or gets rid of one of its hydrogens, and that takes away a unit of positive charge as well. So HF would become F1 minus, right? We're going to take away the hydrogen, and that drops the charge down by 1 unit as well. Phosphoric acid will become H2PO4 1 minus. We haven't talked about it yet in great detail, but yes, there are 3 hydrogens here, but we look at each acid-base donation as a one-time occurrence, just one proton at a time. It's going to be more difficult to take the next hydrogen away from this. Again, in my analogy that I've used about buying someone a cup of coffee, it might be very easy for me to donate my first cup of coffee to a student, but then a second cup, it might be a little harder for me to afford being able to buy that. Let's turn to the base nature then. What is the conjugate acid of each base? So when a base gains a proton, you're going to add a hydrogen. In this case, you're going to be adding it to the nitrogen here. That's where it's going to reach out. So you would have C5H5NH+, because that hydrogen brings with it a unit of positive charge. And in we would get HCN for our cyanide island, and the positive charge that it brings with it cancels out or offsets the negative one that we have there. So the next question, which is the acid, or which species would act as the acid if these were to react with one another? So both HCN and water have the potential to act as an acid. So this would be like me running into another professor at the coffee shop. Who's going to donate? Who's going to purchase the cup of coffee in this instance? So we need some scale, and that's our Ka chart that we would look at. And so the Ka of HCN is 4 times 10 to the negative 10. And for water, the Ka is the Kw, so it's 1 times 10 to the negative 14. So HCN is the more acidic species in this case, and it would be the donor. Water would by default become the acceptor in that reaction. In our next case, it actually is a little bit easier because NaClO has no proton to donate. And so because it has no proton to donate, we immediately can conclude that it must be the base. And H2SO3 is our acid, and you could find a Ka for that if you need it. In our last case, where we have an HCO3 ion here that could be an acid and an HClO, so again we're going to want some Ka values. It's 4.8 times 10 to the negative 11 for the bicarbonate ion, and for hypochlorous acid it is 3.5 times 10 to the minus 8. Again, that's the larger value, so this will be the acidic species in this reaction, potential reaction that we have. Okay. Next question on the sheet focuses on finding some pH values, and these all involve strong species. That's where we started. Later on in the worksheet we'll work with some equilibrium reactions for weak acids and bases. But for right now these are strong acids and bases, and that allows us to quickly determine some of the important information. So we get complete dissociation of hydrochloric acid, meaning that our H3O concentration equals the HCl concentration. So 0.000540 molar. And then the pH is simply found very quickly by taking the negative log of that value. Which in this instance becomes 3.268. Remember that there are 3 significant figures in this concentration value. None of these starting zeros are significant. The 540 are the sig figs, and they lead to the 3 decimal places in our reported p-value. Next problem involves a strong base, but again, because it's strong, we get complete dissociation. So the hydroxide concentration, because there's 1 unit of hydroxide in every sodium hydroxide, will also be 0.00204 molar. So the POH is easily found now, because we have OH, by taking the negative log of the OH concentration. So the POH is first 2.690. To get my pH, recall that pH plus POH equal 14. So the pH will be 14 minus our POH value, or in this case, 11.310. The last one, again, involves a strong acid, or what will be a strong acid, but it's going to involve the most amount of work. Because we're starting with the mass of hydrogen chloride that's being dissolved in our water, we're going to have to do some stoichiometry. So our 3.15 grams of HCl will need to be converted to moles. So we'll need the molar mass of HCl, which is 36.461 grams. This means we have 0.864 moles of HCl. If we divide that by the 2.50 liters of solution that we're making, we come up with a concentration of 0.0346 molar HCl. But because it's a strong acid, that will also be the concentration of our hydronium ion, H3O. And then we can quickly get our pH value as the negative logarithm of that concentration. So that pH is 1.461. All right, our next question focuses on salts. As we discussed in class, many compounds that are ionic salts, one or more of the ions in the salt may have a Ka or a Kb value, and as such, when it gets into water, it will react with water in an acid-base fashion. So when we're asked to identify the nature, acid, base, or neutral, of each of these salts, we want to look for pieces of the salt that have potentially a Ka or a Kb. we have K2HPO4, COCl2, BaNO2, I'm a bit out of order, sorry. NaCH3COO, LiCl, and NH4Br. All right. Remember that we can ignore the behavior of any metal that's in group 1 or group 2 of the periodic table. Those are ions that will not interact with water. So I can get rid of the potassium there, barium, sodium, lithium. And we can also ignore the interactions of our halogens because they are going to not interact with water either. So that's going to get rid of our chlorines and our bromines. So we've already eliminated some things as potential ions that can interact with water. Now, when I look at the remaining ion in each case, the HPO4 on my Ka chart can be found in both columns of the Ka chart. Way down near the bottom, it has a Ka that's very tiny, and then on the Kb side, it's up a little higher, about the middle of the page. So the Ka is smaller than the Kb, which means the basic nature of HPO4- will win out in this solution. Okay? And overall, this should be a basic solution. Cobalt, in this case, is the only ion that could potentially cause an acid-base interaction. It's not in group 1 or group 2, and a careful scanning of our Ka chart shows us that cobalt, in fact, is one of the metals that has a Ka when it complexes with water. By that decision then, or on that basis, we can decide it's an acidic salt, the cobalt-2 chloride. NO2-, all right, it clearly has no protons, so it's not going to have an acidic nature to it. But when you look on your Ka chart, you will find a Kb for that, meaning that the barium nitrite salt will be basic in nature. CH3COO, that would have a negative charge on it when we take away the sodium that's positive bouncing it. Also has a Kb, so this is going to be a basic salt as well. We've eliminated both ions of lithium chloride, lithium because it was a group 1 cation and chlorine because it's a halogen, so this will be a neutral salt, lithium chloride. And then NH4Br would have a Ka for the NH4 ion, meaning it will be an acidic salt. Okay? Now each of these could be used, each that has an acidic or basic nature could be used in an equilibrium problem as well. And if you were faced with one of those problems, the first task would be to determine the nature of the salt, whether it's acidic or basic. Okay, let's turn to the Ka-Kb problems that are included on the chart sheet. The pKa of formic acid. So our Ka chart provides us the Ka of formic acid, which is 1.8 times 10 to the negative 4. The pKa is just the negative log of the Ka. So we would take the negative log of 1.8 times 10 to the negative 4, and our answer is 3.74. pKb of the acetate ion. Again, our K chart has a Kb listed for the acetate ion of 5.6 times 10 to the negative 10. pKb would be the negative log of that Kb value, and that would come out to 9.25. The pKb of aniline. Aniline is not on our chart, but in the book I can find in chapter 15 a small table of K values for Kb values, for some bases, and aniline is listed among them. Its Kb value is 3.9 times 10 to the negative 10. So its pKb, again, would be the negative log of that value, or 9.41. The pKa of the ammonium ion. Ammonium ion is NH4. It has a Ka on your chart, 5.6 times 10 to the negative 10. Thus, the pKa is the negative log of that, or 9.25. All right, our next two questions ask us to make use of conjugate acid-base pairings. The Kb of an unknown base is 4.9 times 10 to the negative 11. Find the pKa of the conjugate acid. There's really two ways that we could do this. There's a relationship between Ka and Kb, that their product is Kw, and then there's a relationship between pKa and pKb, that their sum is 14. So it might be quickest to find the pKb of this base by taking the negative logarithm of its Kb. So the pKb would be 10.310. And then because, again, pKa plus pKb equals 14, the pKa of the conjugate, this is true only for a conjugate pair, will be 14 minus our pKb, or 3.690. That relationship is the one that we want to use for this last problem as well. We're told that the pKb of ammonia is 4.75. So find the pKa of ammonium. Okay? So again, ammonia is NH3, ammonium is NH4+. They're a conjugate pairing there. So this is very quickly found. Simply pKa will be 14 minus the pKb, or 9.25. Same value we had up here, but that's how you could calculate it if you didn't directly have the Ka value. All right. The last group of problems on the worksheet will focus on weak acid-base equilibria. Let's take a little bit more time and room. Let's get these set up. The pH of 0.25 molar formic acid. So we're going to recognize formic acid is a weak acid because it has a Ka on our Ka chart. We used it already, 1.8 times 10 to the negative 4. So the formic acid will interact with water, and we can set up an ice table beginning with 0.25 molar formic acid. Some of that will disappear, and we will produce an equal amount of H3O and conjugate base. We're going to go ahead and use our approximation method in this case. And our Ka is what allows us to solve for x. Just like we did in chapter 14 again for regular equilibria. So I plug in my Ka, 1.8 times 10 to the negative 4. X times x, x squared over 0.25. Multiply the 0.25 to the left, and x, which is the importantly for this problem, the concentration of hydronium ion at equilibrium will be 6.7 times 10 to the negative 3 molar. So the pH is simply the negative log of this, or 2.17. That should internally make sense for you because this is an acid and that's a low P value, a low pH value. Now we're going to look at 0.25 molar aniline. In a previous question, we identified that aniline had a Kb of 3.9 times 10 to the negative 10. It is a base. Our reaction is different than our first problem that we just did with formic acid. Our base reacting with water will not produce hydronium ion. It will produce hydroxide ion. And that's why we need to know the nature of a substance to understand whether we make excess H3O or OH minus in our solution. The problem is essentially solved the same way though. Well, we have a 0.250 initially, zeros for our products, minus X plus X. Certainly have a small enough Kb to use the approximation method. We set up our Kb expression, our ions in the numerator and our base in the denominator. Again, we'll have x squared over 0.250. X is, in this case, when we multiply the 0.25 and take the square root, 9.9 times 10 to the negative 6th molar. Unlike this first problem, though, where that was what we were after for H3O, we have chosen X to represent hydroxide because of the reaction that we have. So this adds a little step to our work. We need to take the negative log of that to get the POH of this solution, which is 5.01, and then the pH is 14 minus that POH value, 8.99. Again, there should be that internal consistency. Once you've identified the aniline as a basic substance, you know your pH should be greater than 7 for that solution. All right, a couple more problems. What is the pH of 0.25 molar solution of sodium acetate? Okay. This is the formula for sodium acetate. Again, this is the acetate ion, has the base nature. We did identify this in a problem earlier with one of our salts. It has a Kb. The Kb of the acetate ion is 5.6 times 10 to the negative 10. So our reaction, we could use that formula, or again, we could set up B, base plus water, will give us OH minus plus BH plus. This table is going to look identical to the table that we had over here, because we're starting with 0.25, small enough that we're going to ignore the minus X on the reactant side. So we'll set up our Kb, and I'm just going to jump right to the numerical solution this time. 5.6 times 10 to the negative 10 will equal the x squared over the 0.25. So our x, in this case, will be 1.18 times 10 to the negative 5 molar. X is representing the amount of hydroxide. Thus, the POH is found by taking the negative logarithm 4.93. And the pH is lastly found by subtraction, 9.07. Again, earlier we had identified this as a basic salt, and we get a pH higher than 7. So that gives us some confidence in our answer. This next question is just a different take on one of the ways we could ask acid-base problems. What percentage of nitrous acid molecules, which would be HNO2, dissociate or react in 0.250 molar HNO2? Okay. So if we set up the reaction of HNO2 plus water, it's just like any other acid, we'll produce H3O plus and NO2 minus. What the question is really asking us for is, what's the change? How much of it reacts right here? Okay? What's the decrease in this? So 0.250, 0, 0, minus X, plus X, X, X. The Ka of our nitrous acid is 4.5 times 10 to the negative 4. So we're very much borderline for what the value, for the approximation method. But let's go ahead and treat this as an approximation method, because we usually do that with our weak acids. Set up your Ka expression and solve. 4.5 times 10 to the negative 4, x squared over 0.25. So x in this case is 9.5 times 10 to the minus 3 molar. Now you could use that to calculate the pH, because that is the H3O, but here we want the percent dissociation, or the percent of reaction. So it will be the 9.5 times 10 to the minus 3 molar HNO2 that has reacted out of the initial 0.25 molar times 100%, and that would be 3.8% has reacted or dissociated. Okay. That's not as common, but it is another way that we can characterize sort of the strength of an acid by this percent dissociation. Okay, one last problem to work on. We have a 0.315 molar solution of an unknown acid. We're given the pH, find the pKa. So we can represent an unknown acid as HA again, plus water, to give us H3O plus and A minus. We're told the 0.315 molar starting value here, and we're also told the pH. The pH of 2.58 is going to allow us to calculate the H3O plus concentration at equilibrium that belongs right there. It would be 10 to the negative pH value, or 2.63 times 10 to the negative 3 molar. Now this goes back to one of our first equilibrium problems that we did in chapter 14. If H3O starts at 0 and ends at this 2.63 times 10 to the minus 3, then it must have increased by that amount. And because these have to increase by equal amounts in our change row, we now also know how much our conjugate base has increased by. And we know how much this has decreased by. And so that would bring this down to 0.312. 2 with the rounding. So our Ka then can be found by substituting these numbers from our ice chart. 2.63 times 10 to the minus 3 would be squared, divided by the 0.312. This should give us a Ka of about 2.2 times 10 to the negative 5. And the pKa of our unknown acid would simply be the negative log of that Ka, which will be 4.66. Okay, that wraps up all the problems on the worksheet. Again, I hope you've taken the opportunity to complete this before I come back from my trip to San Diego for the ACS meeting, so that we can promptly pick up and move on with the remaining topics from this chapter. If you have questions, I'll be sure to answer them when I come back, and I'll look forward to picking up with you when I see you again. Have a good day.